There we go. Polymers. The topic of polymers is huge. That's probably why that slide set that the authors gave me was over 100 slides. And I tried to pare it down, but I couldn't get below 103. So,
yeah.
But that doesn't mean we have to spend a whole lot of time on each slide. Polymers is a real specialty. I mean, there's probably a rivalry among organic chemists, the polymer people and the non-polymer people. I would be willing to bet. Because polymers are so important in our daily lives. There was a time when in human history where everything we had was either directly drawn from nature or modified from nature, like cut down a tree and make a table out of it. Right? They were all natural occurring products. With the advent of modern chemistry and organic chemistry in particular, now we engineer the things around us at the molecular level. And the magic word there is plastics. The polymers is the proper chemical term. All right, this we're going to divide this into 3 or 4 sections. The first 5 subsections we'll be discussing how polymers are made. What's the mechanism behind polymerization? So we're going to look at radical polymerization, anionic and cationic. Ziegler-Natta catalyst is a special type of polymer control, and coordination polymerization comes into there also. So remember what coordination is. If they stick to the definition, coordination is the formation of a bond where both electrons for the bond are donated by one of the atoms. They don't share. Just one atom comes in and doesn't contribute anything. So polymerization can take place that way. They've got ring opening polymerization, and that makes sense because ring opening is usually cyclopropane type. And when the ring is under stress anyway, so just a little bit of nudge and it opens up and you get a reaction. And then there's step growth polymerization. We'll have different examples. One thing to remember is the polymer, many polymers can be formed by more than one of these types of polymerizations. And it just depends on what the exact outcome is. See, polymers are so big, they're so huge, and you can get so many different things like branching or functional groups on polymers that it's difficult to characterize them. So that polymer chemists have their own language, and we're going to only get a taste of it here. All right, then we want to look at modifications. Once the polymer is formed, we can change its chemical characteristics by modifying its side groups. They're called pendants. Or we can even cross-link them. Cross-linking like vulcanization of rubber and tires. That's a cross-linking process. Perms, that's beauty shop. That's a cross-linking. That's why it stinks so bad. It smells like sulfur. They break the sulfur bonds that are naturally there, holding your natural curl, if it is one, and then curl it up, and then they reestablish the cross links with the chemical process, and that holds it in that curl until it grows out. Then there are we'll get into some general aspects of polymer structure and nomenclature, different properties. The relationship between structure and function is essential for engineering different types of materials and their intended purpose. Then we'll look at greening of polymers a little bit. And finally, biological polymers. All right. So these are examples of polymers. Plexiglass, right? You see plexiglass everywhere. Actually, plexiglass is good for some things, and for some things it's not. Whereas we would substitute something like Lexan. And these are, plexiglass and Lexan are proprietary names, right? They're trademarked. So when you say plexiglass, you are probably talking about a particular polymer, but this plexiglass is owned by a company. But I think the patents run out, so you can call it by its chemical name and you're safe. Kevlar, right? Kevlar is a rigid polymer. It's very strong. They say ounce for ounce, it's stronger than steel, and that's probably right. Teflon, polyfluorinated hydrocarbons. Teflon is a particular type, and there's a whole bunch of different types. I used to use polyfluorinated hydrocarbons. Wasn't the original Teflon, but it was a special type of Teflon beaker that you could put on a hot plate and heat it up like you would a glass beaker. It was that durable. But we used Teflon because it wouldn't contaminate your sample. We couldn't even have glass contacting samples. As most glasses, even Pyrex is a borosilicate. So if your sample is supposed to be prepared and you're analyzing for boron, you don't want to do it in standard Pyrex. We also had glassware that was boron free, but that was pretty expensive too. Let's see. Okay, so their polymers are large molecules. That's the first condition. They're very large molecules. And they're a product of linking small molecules, small subunit molecules. I don't know of any polymer that's formed by just adding atom at a time. They're usually pre-existing small molecules, then you link those together. They usually have a regular repeating structure. So that's key to how we're going to draw the structure and eventually naming the polymers. Also known as plastics. Can't imagine the world without them. That's true. Drinking bottles, storage containers, pipes for plumbing, tires, especially tires. During World War II, we embargoed. We didn't just embargo. Now this is going back to World War I. Embargo nitrates from Chile, so that the Germans couldn't make explosives. And that's when Haber came along and took nitrogen from the air, made ammonia, and then just oxidized it, make nitrates, and got your explosives. But we also embargoed natural rubber from South America and from Polynesia, Southern Pacific Islands. And that's why the Japanese were after it too. They wanted to take over all that area between Vietnam and Australia because of the resources. There was oil in that area, and there was rubber for their tires. But we came up with synthetic rubber, and we're going to look at one of those much later that are added to tires to substitute for natural rubber and to modify the physical characteristics of your tires. Synthetic fibers, right? Let's see. I like cotton, when I can get it, but there's something to be said for synthetic fibers too. And that's enough. Our clothing, actually, we've got exercise clothing that is not just synthetic fibers anymore. It has embedded nano molecules in it to modify the properties. These are some trademarks: the plexiglass, Kevlar, Teflon, Lexan, or just to name a few. And each has its special properties. Okay, the first type of polymerization is radical polymerization. Here we're talking about free radicals. Remember, a free radical is any molecule, any ion, any atom that has an unpaired electron. That makes it extremely reactive. So we're going to use styrofoam as an example. And the polymer made from styrene is polystyrene. It was invented in the 19th century. By a lot of these have been created by accident. But once we figured out how to control the manufacture of them and produce given end products, there are some polymers that you can make with an open lattice structure, so air can move freely in and out. And there's some that have closed cell structure, and those, and you can do that with polystyrene, and you can do those in such a way that you trap gas in the matrix, and then you can use that for insulation. So we got packing peanuts and we got styrofoam cups. We'll talk more about this when we get to the green section at the end. I mean, they have good physical properties, but they are not green friendly. Okay, here's what we mean by radical polymerization. Well, first of all, the polystyrene is composed of this styrene molecule, which is simply a benzene ring. And then it has a vinyl group on the side. So vinyl means like that. So let's see, 1, 2, 3, got a hydrogen here, and we've got 2 hydrogens there. So that should be styrene. And the polymerization takes place in here. So this is a pendant, a side group that hangs off, and you can see them, they're hanging off the side of the carbon chain backbone. So we can go from a monomer, the monomer, and these terms have specific definitions. The monomer is the small molecule before polymerization takes place. So it's not the same as a, well, I forget the term now. We'll get to it. So the monomer is what you start with, then you polymerize it, and you get the polymer. And it can go on for thousands of units. Okay. Well, there's the definition for monomer. Mono means one and meros means part. So it's just one part. And polymer means many parts. Okay. So the process is called polymerization, of course. Okay, there's our, on this slide, we have the polystyrene at the bottom. It has a backbone and it has pendant groups. These are usually fairly easy to identify, the difference between the backbone and the pendant groups. Now, these pendant groups have a decided effect on the physical and chemical properties of a polymer. This huge phenyl group hanging off the side will have a limitation on bending and rotation of the bonds in the molecule. All right, for this, let me, there we go, get that out of the way. Okay. We've identified styrene as the monomer. Okay. This is a type of vinyl polymer. Now, you can get, if you have this part of the molecule, then you can put different things off here, and change its properties, but the polymerization takes place there. Polyethylene. If this were a hydrogen and we polymerized it, that would be polyethylene, because this is the ethylene molecule. So that's known as a vinyl polymer. The polymer chain, or the main chain, is the backbone. And then we have the pendant groups. For this particular one, and for all other vinyl polymers, the backbone is only carbons, only carbon atoms. That's not always the case. This is just one type. You can have heteropolymers too. You can intersperse, most commonly intersperse oxygens. Okay. Side groups or pendant groups, we mentioned that. Pendant means hanging, of course. Okay, so we can't draw that formula out. So what we try to do is we take what we believe to be the structure with repeating units, and we find out what's the smallest repeating unit. It's kind of like when we were looking at unit cells in chapter 10 and 11, I think. What's the smallest repeating unit? In this case, the repeating unit has 2 carbons and this side group. That's the smallest repeating unit. But notice the double bond is gone. We used the pi bond of that double bond to form a bond with the next repeating unit. That's why you don't see it there. And one way of expressing it is to take the repeating unit, put it in parentheses, and then use a subscript N for the degree of polymerization. In other words, how many of those things do you have in a single polymer? And those numbers can be massive, 1,000, 2, 3, 4, 5,000 on up. Okay. So this is the repeating unit as opposed to the monomer. Monomer is before the polymer forms. The repeating unit is the smallest unit that can represent the polymer in our condensed form. So these are two different concepts here. That formula at the bottom is degree of polymerization, and the value there is designated as an N, a subscript. So and this is approximate. Polymers, we have some control on how much polymerization you can get, go along a certain way, and then stop it. But you still get a range of polymers. And we'll look at those a little later, how to determine what your range of polymer size is. Because that also dictates the chemical and physical properties of the polymer that you're trying to create. So you take the molar mass of the polymer on the average and the molar mass of the repeating unit and divide them. And you get this degree of polymerization, which is represented by the number that we substitute for N, subscript N. So if we look at, for example, we take this polystyrene and we say, okay, our polystyrene can be represented by C28H40. And I have to take their word for it, which has a molar mass of 520. And then we take the molar mass of the repeating unit and divide them. What do we get? Okay, the repeating unit is C8H8. And divide the two, and we get what, DP of 5. So if we only wanted to represent that 40 carbon unit, then we would draw that repeating unit and a subscript of 5. Okay. All right, this draws the distinction between the monomer and the repeating unit, and I've already done that, so I don't think we need to go into this a whole lot of depth. Just to emphasize that the monomer undergoes a chemical reaction, so it is necessarily changed from its monomer structure to its condensed repeating unit. All right. Oh, for all vinyl polymers, you have a repeating unit that's only 2 carbons, and then the pendant groups. So that's helpful. If you know it, you're making a vinyl polymer, then you know what the backbone is going to be like. And the repeating unit, all you have to do is figure out what's the pendant. Okay, I'm not going to spend time on this one. Okay, radical polymerization of styrene and other vinyl polymers. Okay, this is speaks of a mechanism. Radical polymerization. Okay, when there are steps, we divide the polymerization into steps. One is initiation. How do you get it started? And that's characteristic of radical polymerization. We get it started with a free radical. Right? We can put this stuff in the reaction mixture and bring it up to a temperature, and maybe some reactions will occur, but the polymerization that we want won't occur until we spike it with our initiator. And our initiator in this case is benzoyl peroxide, right there on that arrow. Right? We add heat, and we have benzoyl peroxide. Let's see. Got these 2 phenyl rings, but now they're benzyl because we've got a carbon here and carbon here, and oxygen in the wrong direction. Oxygen's here. That makes it a peroxide. And then there. So these oxygen-oxygen bonds are notoriously weak. So all we need is just a little bit of heat, and we will break them. And when we break them, this breaking is homolysis, which means one electron goes this way, one electron goes that way, and that produces our free radical. So once we get that benzoyl free radical, that's what initiates the polymerization.
Free radicals bad.
In your body they are.
Yeah.
Yeah, right. And natural processes in the cells produce free radicals of various types.
Do we get free radicals from the sun, don't we?
Well, they can produce free radicals in your skin.
Yeah.
Yeah. Right. All you need is enough energy to knock an electron off a molecule, leave one behind, and you got a free radical.
Yeah.
And it makes them very reactive. So that's why you see so much marketing with respect to free radical scavengers. Free radical scavengers usually include lots of double bonds, like unsaturated fatty acids are good free radical scavengers. Carotenoid pigments, they're loaded with double bonds. They will scavenge free radicals. Diets that are that have lots of vitamin E in them, right? It has lots of double bonds. And then there are certain atoms, so elements that are good free radical scavengers. Oxygen is a free radical producer. Simply because the bond between these 2 oxygens right here, well, it's reactive enough with the paired electrons, but all we have to do is break those in 2, right? And you've got these 2 and these 2. Okay, 2 electrons go over here. along with the two that were already there. 2 electrons go here, well, 2 there. But in fact, those 2 electrons are not paired. Right. If we draw the electronic structure, we get these electrons in the p orbital. Right, go 1, 2, 3. These are S, 1, 2, 3, 4. 1, 2, 3, 4. So we have these 2 unpaired electrons. Not to draw the whole structure, but just to make a point. So this is what happens at high altitudes, right? When the ultraviolet radiation from the sun is really strong, oxygen in the upper atmosphere gets split like that, and then that free radical reacts with another oxygen molecule and forms ozone, which in itself is reactive. Radical chain reaction mechanism. Okay. That was the overall equation. So how does that happen? Well, there's our benzoyl peroxide, the initiator, and we put it in the mixture, and nothing's going to happen until we heat it. We add a little heat. That's enough energy to break that bond and form our free radicals. And then those radicals start the process. Well, actually, I left a step out. What tends to happen is the phenyl group breaks off from carbon dioxide. And because carbon dioxide, this breaks off here, forms carbon dioxide, and leaves this phenyl free radical. And since this is a gas, you get some bubbles when you first start the reaction. You see those bubbles. Once you get these free radicals formed, then the reaction takes off. And it doesn't go back because the gas is removed from the reaction mixture. So it drives the reaction that way to produce this, and that goes away. So your reaction as presented here goes all the way to the right. Okay, this is the initiation step. This is what gets it started. And then once it's started, we look at how it propagates. So we have the initiation step, the propagation step, and then the termination step. Sometimes they terminate by themselves. Some reactions do that. Some polymerizations do terminate autonomously. But very often we have to do something to terminate the reaction, other than just letting it run out of reactants, because we want control over the structure and the physical and chemical properties of the polymer. Okay. Right. Homolysis is the process that gives us the free radical. Okay. So what does that free radical do? Well, first thing it does is it bonds with the vinyl carbon here. So if we have this free radical, what am I doing? We have this free radical here. Then we get the we donate an electron from both sides. One electron comes from here. Let's see. Does that go to the? They put it out into space. So it goes out here like that. This one comes in here like this. We form a bond between that one and this one. There. And then there's another electron that's in that pi that goes over here. So that's a lone electron that forms a free radical on that end. Right, so the pi bond is gone. Now we have a bond here plus a free radical. Oh, I put it on the wrong one, didn't I? Yeah, I did. I put it on the wrong one. It's not this one. Form bond. This one. Okay. So now that we have that free radical, it just keeps propagating. And that free radical will attack another vinyl group and then form another free radical, and it'll just keep going until we quench the free radical somehow. Okay, let's see. Yeah, single barbed arrows, single electrons. Okay, so we just continue to get propagation, step after step after step. And this is also known as addition polymerization, which just means that the monomer is added to the end of the building polymer, just one at a time on the end. That's addition polymerization. This is one type of. We also call it chain polymerization, right? So these names are kind of interchangeable. This is what it would look like if you could see it at the molecular scale. Just you'd see the chains growing, and they just grow in length, right? And no branching. There are things we can do to make them branch, but in this case, we're saying that we don't want branching, right? They just continue to grow from the free radical reactant end. Now, I suspect that the reaction rate will slow down over time, right? Like we learned in kinetics, if you reduce it depends on whether it's a zero first or second order. But the reaction in general will slow down over time, probably, as you reduce the number of reactant monomers. Okay, how do we terminate? Well, one way to terminate is to get two free radicals, right? Say this one now has there to get the growing polymer. No, that's not it. It's up there. Get the growing polymer to combine with another one. The two ends meet and they quench each other. Those two free radicals form a bond between those two carbons, and that terminates the chain. We got no radicals, so we don't get any propagation. Okay, two types of termination by combination, right? That doesn't seem like we have much control over that one, though. Or termination by disproportionation. Okay, disproportionation, the only time I've heard of disproportionation was with, let's see, where we had, if I can remember the reaction. It was a redox reaction. I can't remember it. I just know that we have one molecule going in two different directions. That's disproportionation. So I assume that they're gonna work from that proposition. Radical coupling is coordinate combination also. All right, so this is by combination, right? And that's not telling us something we didn't already know. All right, I'm not going to go into those details. That's too much math. We're trying to hit the high points. Okay, disproportionation. Any reaction in which two identical species react to produce two different products. Okay. To identical species. Okay, yeah, that fits. Yeah, with my inorganic disproportionation. So if we get these two polymers with their free radical ends, and we transfer a hydrogen from one of them and form a double bond with the other one, that reconstitutes the vinyl end, what used to be the vinyl end on one polymer, and then just a hydrogen end on the other one. That's disproportionation. So either way can terminate a polymerization. They produce closed shell species from radicals. So these steps are pretty quick. They're not rate determining. Which one dominates depends on the nature of the monomer and the reaction conditions. So these can be modified by recipe. And I'm sure organic chemists love that. Gives you control. All right. Right. These are the two molecules produced by disproportionation. One has a hydrogen and a phenyl end, and one has a vinyl and a phenyl end. And that shouldn't alter the characteristics of the polymer that much, just to have those just slight differences at the end of the molecule, considering that the molecule is a monster. Then I wouldn't expect the physical or chemical properties of the polymer to be much different if you could isolate one from the other. Okay, end groups. Whatever is on the end when you terminate your polymer. You have repeating units, and then the end groups are usually artifacts from the termination step. Let's see. Okay, it's drawing a distinction there between the disproportionation end groups. Right. And for most polymers, those end groups contribute very little to the polymer structure because they're just such a small part, just at the ends of the polymer, and that's it. Okay. So usually, and in fact, very often the end groups are just left off of the of that repeating unit structure, drawing the structure with repeating units. Usually just leave the end groups off. I think we're going to get an example here. Let's see. Head to tail addition or head to head addition. Okay, we're getting into regiochemistry here. Right. Where does the free radical attack? Right. If you get those the free radical end of the building polymer and it attacks the vinyl group here, it could either attack the vinyl group there or there. Either one of those carbons are fair game, but they're not equally as likely. A head to tail addition is the more likely one. And the primary reason for that is steric hindrance. Right? If you try to attack the one that's attached to the phenyl group, which would give you a single carbon between two phenols, there would be a lot of steric hindrance there, and it's not likely. That would be a very, very minor product. Okay. Styrene is an unsymmetric vinyl monomer, which just means it has a distinct head and a distinct tail, and they don't act the same way. Right. Head to tail versus head to head. And here's an explanation for steric hindrance. Right, so a head to tail is more likely. Well, there are two reasons, actually. It's steric hindrance and resonance stabilization of the free radical. So if you have a head to tail addition, you have the free radical now is right next to the phenyl group, which resonance stabilizes it. Right. If you have the if you have the free radical formed, well, there's a free radical Now let me see. All right. Yeah. Okay. If you have a carbon in between the two phenyl groups, like in the top one, then that puts the the radical next to the phenyl group, which stabilizes it. If you do a head-to-head, then you have the free radical on a primary carbon, which is less stable. Yep. So that one is the head-to-head addition is not as likely. There's also the possibility of stereochemistry. You're creating a new chiral center because you've got this long polymer end building out here, which would be and on that carbon where the bond is formed, that carbon now has a hydrogen, it has a phenyl group, it has a long chain to the left and a radical on the right. So you have a chiral center there. So your molecule, depending on which side it attacks, you can build into your polymer lots of stereochemistry. And here's an example, and the naming convention for, or descriptive terms for the different types of polymers that can form. Now, if you can control the chiral center and how it forms, then you can get a different type of polymer out of the same monomer. Right? And here we have, this example is a polystyrene again. So the way the chiral centers develop and the way they're distributed in the molecule defines the tacticity of the polymer. Tactic means touch. Atactic configurations, they're all random. Right? There's no rhyme or reason to it. And to get those, all you have to do is treat the monomer with benzoyl peroxide. And it just happens. Chiral center, you attack from one side or the other side, it's completely random. Isotactic is a configuration that gives you the same stereochemistry for every carbon in the chain. Every chiral carbon in the chain has the same stereochemistry. That's isotactic. And this is accomplished using that Ziegler-Natta catalyst. We'll look at that a little bit later. Syndiotactic are those that alternate on successive units. And this Ziegler-Natta catalyst can also be used. You just have to modify the conditions to give you that. And we see examples at the bottom of what you can do with each one. Products that are possible. Okay. Now I mentioned size distribution of polymers before. How do we know? We get polymers of varying lengths that are formed during the process, and we try to control it. We try to maximize one. Maybe we want a certain mixture, but the control is key. And then quality assessment is by way of determining what distribution of molar masses do you have. That tells you you got this length or that length or just a huge length. And here we have a representation. On the y-axis is signal in millivolts, and on the right is time. So this is referencing a procedure called, I think it's electrophoresis. Gel electrophoresis. Where is it? Samples determined by gel permeation chromatography. Okay. So just think agar as your gel, and you put your samples in one end and you get them to migrate through the gel. very often what you do is you use a strong electrical field so that the polymer becomes charged and it moves. Well, gel permeation means that the bigger ones move slower because there's more hindrance moving through the gel, and the smaller ones move faster. So the amount of time it takes to move from one end to the detector end is a measure of molar mass. And you do have to calibrate it. Usually put a standard in there that's notably different than the others, so that you can tell, all right, when this peak shows up, that sets the point at this molar mass, and then beyond that is incremental by time, and you can calibrate it. Sometimes you put more than one standard in there, maybe a low weight standard and a very high weight standard to bracket it in. And the bigger ones, now why does this one, that just contradicts what I said. The bigger one comes out quicker. All right. Size exclusion. Oh. Okay. All right. Back up. The gel has cavities in it. The smaller molecules can migrate into those cavities, which means they go in there rather than traveling along the line. So the smaller ones take longer because they have a longer pathway. They go into the gel, out of the gel, in and out, in and out. Whereas the big ones, they can't go in, so they just go right on through. Okay. That's gel permeation. That's why the heavier one shows up first, and the lighter ones show up later. It's like the description of chromatography I gave the class, and I think it was the 211. You have a stationary phase and a mobile phase, and the affinity of the molecules that you're trying to separate determines whether they move fast or slow. If they have a strong affinity for the stationary phase, they're going to hang on to it longer and not move as fast with the mobile phase. So the stronger affinity with the stationary phase is going to come out last. All right, anionic and cationic polymerization. This just means that depending on what we use as an initiator, determines what type of polymerization we have. Free radical, we did with benzoyl peroxide. If we use butyl lithium, then we get this negative ion with a lone pair of electrons, and they attack that out the carbon furthest from the styrene, furthest from the phenyl group, and what that does is it moves electrons in pairs now. So the pair on the pi bond is sent over to the carbon next to the phenyl group, and that propagates to the next one. So this is definitely head tail for propagation. And that full negative charge, I would be willing to bet, is stabilized by resonance with the phenyl group. How do you terminate it? Well, one way to terminate an anion is to give it a hydrogen, right? And form a bond with a hydrogen. So you just use an acid. Just hit it with an acid and it'll terminate the reaction. This seems like a pretty good way to terminate that type of reaction. You might want to use this instead of the benzoyl peroxide. Now, you've heard of benzoyl peroxide before, haven't you?
Yeah.
Mm-hmm. Acne cream.
Yeah.
Yeah, it's very good at killing bacteria. Probably because it only needs a little bit of heat from your skin to break that molecule, form free radicals, and they attack the bacterial cells. And your skin protects the rest of your cells from the attack of the free radical. Okay, so we terminate it with an acid. How about cation polymerization? With a cation polymerization, the attack is not from the initiator. The attack is from the pi bond on the cation. But that leaves us with another cation on the growing polymer, and then the monomer attacks that cation. That's a propagation step. So we're left with carbocations. Once we get started, it's based upon the carbocation. And of course, this is going to be head to tail polymerization, because we know from experience that that carbocation is stabilized by the phenyl group. Okay, so how do we terminate it? We terminate it by giving the carbon a complete octet some way, right? In this case, we take a chloride ion off of that molecule, and how do I name it? Your guess is as good as mine. Trichloroborate. But that stopped the reaction. Once you've given that carbon, we capped it off with a chlorine N group. That stops that one. So anionic polymerization is used if the electron withdrawing groups are attached to the carbon-carbon. And cationic, the electron donating groups are attached to the carbon-carbon. So that makes electron accepting groups would be acids, Lewis acids, and electron donating groups would be Lewis bases. So this is one of those examples where organic chemists like the concept of Lewis acid, Lewis base. All right, ring opening polymerization. So here we have an epoxide or an oxyrane, and polyethylene oxide is the result. Let's see. Well, that's enough said about that. Just know it happens. Step growth polymerization. Okay. This occurs when molecules through a mixture join with any other molecule that has an appropriate functional group. So rather than chain growth polymerization, where you just add to the end of your polymer, this requires that your monomers or the growing polymer has active functional groups on one or both ends of the molecule. So you can grow from both ends. You can take two growing polymers and they can attach and form a big one just like that. So this step growth occurs in steps. A perfect example of that is nylon, where you have 1,6-dioic acid or adipic acid, hexane 1,6-dioic acid, and hexane 1,6-diamine. And you form an amide bond. That's the bond that builds nylon, is the amide bond, where you have the carbon like this, nitrogen, that, and the rest of the molecule. That's the amide bond. That's the basis of nylon. I think it was invented just prior to World War II. And it couldn't have come at a better time, because when the war started, we lost access to silk production out of the Far Eastern sources. So nylon substituted for silk in our parachutes primarily. And now we put it in everything. I mean, not just stockings. I mean, we put it in tires. We put it in, I've got a tent at home. It's packed away. I used to camp a lot, which has what we call ripstop nylon. It's a nylon shell, but it has these heavy threads. You've seen those that are crisscrossed through, built into the structure. And if it rips, it gets to one of those heavy threads and stops. Okay, this step growth polymerization in the of nylon is also called, it's a type of condensation polymerization. A condensation is one where when the bond forms, a small molecule is expelled. In this case, water, which is very often the case. Is water is a product and it's expelled from the reaction to form the bond. So, and that makes sense. If you have let's do it this way. If you have this one, like that, and then you have an amine here. See, how many of these do we have? I think 2. Carbon. And then go like that. Then I look at it this way. You take that right there. There's your water. And this bond then forms like that. That's a condensation reaction. Our cells use them all the time. When we form when we form true fats, take the glycerol and add fatty acids to it, we expel water molecule. I think that's what they call metabolic water. And that supposedly is why camels can go such a long time.
Plus they can eat cactuses.
Well, yeah, that too.
That's crazy to me.
They must have some tough lips.
They have like these little tentacle looking things that protects the inside of their mouth. Oh, it is crazy looking.
Okay. So this step growth polymerization, if we were making nylon, we'd take 2 molecules, right? There, got that one. Then we can take 2 more of those molecules and it just keeps, and they tend to grow faster, I think, because you can put big things together. You just need active groups. I'm not going to spend any time on that. New chain, 2 chains growing, step growth. Okay, this just shows the formation of polyethylene terephthalate, PETE, which is pop bottles. That's what they're made of, PETE. And in this case, call your attention to the previous one, nylon, and this particular one. Now we have not just a heteroatomic backbone. We've introduced in nylon, we introduced nitrogen and oxygen, part of the structure. And this one, it looks like it only has oxygen and carbon along with. Right. And this is a acid catalyzed reaction where we expel, I think we probably expel water. Yep. There's OH from the terephthalic acid and the hydrogen from the ethylene glycol. And we've got reactive groups on both sides of the terephthalic acid. We've got carboxylic acids on both sides. The ethylene glycol, we have hydroxyls on both ends. So we have reactive sites on both sides of the molecule. And we can react one side of the molecule and then the other side can react with something else. And it just gets big in a hurry. Okay. I don't think we need to spend a lot of time on there. Other step growth polymerizations, right? Isocyanate functional groups on either end of this toluene diisocyanate and the ethane 1,2-diol. You can get reactions with those. And this forms polyurethane. Polyurethane's been around for a long time. Yeah. They used to, and they may still do it, blow it into walls of trailers. it would come out, the nozzle would combine those two reactants in the application. They'd stick it in the wall and blow it, and it would just balloon. Okay, what are the let's see, is this a condensation reaction? Let me look. Let's see. Carbon, oxygen, get rid of hydrogen. Well, I see it's missing a hydrogen from the ethane 1,2-diol. Nitrogen, carbon, oxygen forms another oxygen. Oh no, the hydrogen ends up on the nitrogen. So it doesn't, it's not a condensation. Right? We're not producing any small molecules out of this. That was just from my curiosity. We've at this point we've only talked about linear polymerization, just forming a single backbone. But you can also get branching. Branched polymers add a certain type of they change the physical and chemical properties by branching. Now, this is true for synthetic polymers and for natural polymers that we're going to talk about at the end of this series of slides. Okay, obviously, linear polymers have a single continuous main chain. Branched polymers have, at certain points along the chain, branch off another growing polymer. Branching can occur during chain polymerization if the reaction site becomes located somewhere in the middle of the chain. All you need is a reactive site. So we're not going to say any more about that. We are going to talk about network polymer. Bakelite is our example here. So if you have phenol and formaldehyde, you can form a polymer that forms in 3 dimensions. We've only got 2 dimensions here, but it can go in 3 dimensions, every which way. And bakelite is it's been around for a long time. In fact, it was the first polymer ever produced commercially. It branches extensively. And in fact, the branching is so high, you can't detect any linear structure anywhere. You can't say this is the linear backbone and this is a branch. It's just, it branches everywhere in 3 dimensions, which contributes to the fact that it, at room temperature, it's a solid. I mean, it's like a ceramic. It's so solid. This is called a network polymer. It's essentially a single, very large molecule, just one molecule. Kind of reminds you of diamond, only it's not as valuable. Okay, it was developed in the early 20th century. And because it's very rigid and it's electrically non-conductive, we find it used early on in electrical components. Like if you can find parts of the country, older rural parts, and you can look at the power lines and you see these.
The glass tops.
That's a substitution.
Oh.
Right. They did use glass, but they also have these like this, and the wire would come along like that. They just tie the wire to it.
Yeah. I think I've seen this.
But these bakelite ones should be white.
Okay.
If you see any white ones, or maybe off-white with weathering, then those are insulators that support the wires.
Yeah. Now the glass ones, because we have a few, they were blue and purple.
Uh-huh.
Yeah.
And they're manufactured to be non-conducting, of course. And they have to be very stable at high temperatures also, which is right up bakelite's alley. Some kitchenware and billiard balls were made from Bakelite. Okay, now I mentioned earlier that what you can do is once you get your polymer formed, if you want to change its chemical properties or its physical properties, you can modify the side group. That's one thing you can do. The pendant group can be changed. So maybe this post synthesis modification is the proper terminology. So if we form a polyvinyl acetate, which is Elmer's glue, and I use that for demonstrations. We take polyvinyl acetate and boric acid and make bouncy balls with it. So the kids, they get to put gloves on and make a mess on the table with their Elmer's glue and boric acid. and then take it home and torture their parents with it. But if we hit this with a methyl oxide, then what we can do is strip the acetate off of there, turn it into an alcohol. Now we have polyvinyl alcohol, and that's what the those little dishwashing and laundry pods are made of. That material, that plastic outside that holds the ingredients inside, it's water soluble. So once you take that and throw it into your machine, when the water hits it, it dissolves and releases the ingredients. Now, there's been some complaints about remnants of polyvinyl alcohol found in the food and water supplies because so much of it being used now.
Yeah.
Okay, that's a post-synthesis modification. All right. Here's another example. If we take vinyl alcohol and it tautomerizes into acetaldehyde, which is more stable, right? The enol form is always less stable than the keto form. So it tautomerizes into the keto form, and then we get the keto. We get, let's see. Do I have any? I don't have any discussion of that one. So that our monomer is vinyl acetate. Okay. Okay, we have to form the vinyl acetate first from the vinyl alcohol and the acetaldehyde. But if we put those two together, then we get enough of them tautomerizing, so now that they can bond together and form the vinyl acetate, which is the monomer. Then we hit it with benzoyl peroxide, and we get a radical polymerization. Polyvinyl acetate. Oh, that's the one we had on the page before, wasn't it? So that's how polyvinyl acetate is formed. Okay, polyether ether ketone. PEEK, PEEK, call it PEEK. We used to use PEEK tubing with our high pressure liquid chromatography instruments because it's very rigid. It stands up to very high pressure, and it's easy to work with to make connections. And this is what polyether ether ketone looks like. So the subunit actually has two ethers, right? Ether, ether, and a ketone. But they left out this polyether ether ketone is, I would call it a trivial name because it doesn't include the phenyl group. The problem with, excuse me, the problem with trying to make PEEK from the monomers is that as it grows, it tends to crystallize. because it has that rigid backbone, those phenyl groups. So, and the neighboring polymers will associate with one another, and they won't form covalent bonds, but they will form the intermolecular forces that cause it to crystallize. So the way around that is to add tertiary butyl groups to the monomers. They don't interfere with the polymerization, but they keep it from crystallizing because that bulky group out there keeps the molecules from getting close to one another. So once you've got the polyether ether ketone with its tertiary butyl group on there, and you've got the ketone, you've got the polymer, then you strip off the tertiary butyl group, right? With get the name. I had it a minute ago. I thought I had it. Toluene. That's it. You use toluene, and that substitutes the tertiary butyl group for the methyl group. And that modifies the peak. Now, you don't care if it's solid now because you've got the peak formed of the proper length that you want, and then you treat it. You run it through a post-synthesis modification, remove that butyl group, and now you can proceed with your peak polymer. Cross-linking. Cross-linking can occur between neighboring polymer chains, and it tends to increase the viscosity, or sometimes even make it into a solid. Increase the viscosity of your polymer, and has an effect on temperatures, melting point temperatures, and other transition temperatures that we haven't discussed yet. So in this case, we're cross-linking with boron. And I think that's what happens with my polyvinyl acetate in the Elmer's glue. It forms this boron cross bridge. Yeah. And that makes, well, there we got a picture of the what do they call that? Slime?
Yeah. Or that blue blood? Is that what that is? I don't know.
I'm not sure. It's some kind of slime.
There's just one kind that you can make, and if you like let it just sit there, it'll run through. But if you hit it like hard, it just hardens.
Oh,
and then you let it set, and it just falls back through.
Yeah, that's a non-Newtonian fluid.
Yeah.
Yeah. You can do that with see, what do they use? I think sometimes they use flour.
I was gonna say, I think it's cornstarch.
Or cornstarch, water of a certain composition.
Yeah.
And I've seen demonstrations, they have a tray as long as this room.
Mhm.
And it's got that stuff in it. And somebody with bare feet comes running across it. As long as they're slapping it with their feet,
Yeah.
it holds them up, and they just run from one end to the other.
Yeah. I've seen where people like fill like potholes and like run cars over it.
Yeah. But if you go slow,
Yeah. You sink.
A second way to cross-link is this polyvinyl alcohol. You can cross-link it with formaldehyde. That's what that CH2O is. That's formaldehyde. Okay, natural rubber. Okay, natural rubber is a polyisoprene. Remember our discussion of isoprene? Isoprene is like this, it has 5 carbons. So there's 3 of them. And then we have that one and that one. But there's a double bond there, and I think it's right here. So that's isoprene. That would be our monomer. And then natural rubber, of course, is formed in by certain plants. It's a polyisoprene. The problem with it is you remove a lot of the water that you get from the sap that you drain out of the rubber trees. And then it forms this kind of a sticky mess. It's hard to work with. So then if you want to stiffen it up, make it usable, you cross-link it. And that's what, what's his name? Goodyear. That's what Goodyear did, Charles Goodyear. Actually, he did it by accident. He was making his wife mad, though. He's doing all these experiments in her kitchen.
Oh, yeah.
And using
Got real sticky and
using her frying pans. You know.
yeah.
And he accidentally dropped some rubber with sulfur on the hot surface, and he noticed a change in its physical characteristics. And then he went off, studied that, and found a way to vulcanize natural rubber and make it useful in products like raincoats and tires,
Yeah.
galoshes. Up to that point, any tires with natural rubber in them, I mean, if you're not on perfectly smooth, non-aggressive pavement, it will eat your tires up. My former boss said I think it was his father, no, his grandfather, had put some new tires on his Model A at Ford. And then this is in Louisiana, and a lot of the roads down there are based upon these little oyster shells. They call them rangias. And you can just dig them up. They're beds and beds and beds of them that accumulated over thousands of years. You dig them up and you can make your roads out of them. But these shells, they have sharp edges on them. So he ran from I think Shreveport area up in the northwest corner down to Baton Rouge on those roads. And by the time he got to Baton Rouge, his tires were shredded.
Yeah.
So this vulcanization makes the rubber more durable. Now, this is vulcanizing natural rubber, but the process itself can be conducted with other polymers as well. Polysulfide bridge. All right. Okay, this just summarizes polymers. They can be classified according to the type of the main chain. Is it pure carbon? Is it a mono carbon only chain, or is it a hetero carbon chain? What type of functional groups does it have on them on the main chain? What types of monomer was it formed from? The number of monomers that are used, right? There are more than that. Polymer structure, you can have side groups. Maybe they're including that in functional groups too. So classify the main chain, only carbons. Or you can have hetero chains, carbon, nitrogen, in nylon, for instance. Okay. Hetero chain polymers or carbon chain polymers. All right. So there's PETE, which is a polyester. Okay. An ester, you remember what an ester is? Start off with carboxylic acid, and you bring it in, you react it with alcohol. That, and you eliminate water and form the bond here with there. That's an ester. This is a polyester. And a lot of our synthetic fibers are polyesters.
Yeah.
Let's see. The functional groups are responsible for linking the monomers together. That's true. Polyethylene terephthalate is a polyester used in carbonated beverages bottles. And I use those in my Boyle's law experiment. Let's see, that must have been first semester. You didn't get Boyle's Law.
I'll get it in the fall.
Oh, that's right.
Yeah.
Yeah. Yeah, we use these bottles because they're very strong. They're clear, transparent, so you can see your little syringe in there with the trapped air in it. So as you increase the pressure in the bottle, syringe shrinks, and we show the relationship between pressure and volume. But PETE is very strong, and it's transparent. It doesn't react with most things. It's impermeable to gases. Let's see. I'm not going to mess with that. Okay. Classification by type of monomer. Okay. We can form polymers from different monomers. So if we look at this acrylic acid, right, acrylic acid has a vinyl group on it and a carboxylic group. So you put those two together, that's your acrylic acid. And if we form a polymer out of that, we get polyacrylics. If we have a methyl methacrylate, so we have the acrylic, and now we've got, instead of a hydrogen, we've got a methyl group attached to one of those vinyl carbons. Then we get a methyl methacrylate, polymethyl methacrylate. That's plexiglass. And then we have acrylonitrile. So instead of the carboxylic acid, we have a nitrile group attached. And these are all vinyl polymers. They're built the same way. They just have different side groups. This polyacrylonitrile. I'm trying to think, what's super glue? Super glue's in there somewhere. Right? As it cures, it forms a polymer. I want to say it's polyacrylonitrile, but I wouldn't swear to it. Polyolefins. Polyolefins are all carbon backbones, only carbon backbones. If we form the polymer from ethylene or ethene, we get polyethylene. If we form it from propylene, right, 3 carbons, then we get polypropylene. If we form it from buta-1,3-diene, we get cis-polybutadiene. Now, we haven't talked about it yet, but this buta-1,3-diene can be polymerized with, let's see, what is it? I forget the other monomer. You can have 2 different monomers and put them together to make a copolymer. We'll talk about copolymers in a minute. Okay, comparison of homopolymers and their descriptions. Homopolymers are synthesized from a single monomer. So we get this polymethyl vinyl ether. That's one we hadn't talked about yet. We get polyolefins. Polyolefins are used a lot in carpets. Let's see. And heterochain polymers. Here we go. 1,4-dichlorobenzene with sodium sulfide forms a heterochain polymer. A polysulfide. Imagine that. Now for copolymers. All right, copolymer is a specific definition. If 2 different monomers are polymerized together and each monomer is capable of undergoing self-polymerization, then the resulting polymer is called copolymer. So in our previous example, that buta-1,3-diene would polymerize itself to give us, must be on the previous one, to give us polybutadiene. Right? So it can polymerize itself. But if and the styrene, we've already seen that polystyrene can be formed. So they can independently form their own polymers. If you put them together and form a polymer with those 2, then you get a copolymer. the nitrile in these gloves, nitrile is a copolymer. All right, this styrene butadiene rubber. I wonder if that's nitrile. Let's see. It is a copolymer, right? Styrene butadiene diene rubber SBR is produced. Used in World War II as a suitable replacement for natural rubber. Okay, so this is our substitute for natural rubber. Nylon is synthesized from two different reactants, but each reactant, adipic acid, cannot polymerize, and hexane 1,6-diamine cannot polymerize. So that's not a copolymer. All right. Nomenclature. All right. The IUPAC name for a polymer is based upon its repeating unit. So we start with a monomer and make a polymer, or we may start with two different monomers and make a polymer. And the trivial name may include the monomer, like polyethylene. That would be a trivial name. An IUPAC name would take that repeating unit. Polymethylene would be the correct IUPAC name. But most people don't recognize that one. Polyethylene is more recognizable. All right. Some of them have trademark names. Right. So we have IUPAC recognizes trivial names for approximately 20 common polymers. Polyethylene is probably one of them. The names for homopolymers follow a polymonomer format. If the name of the monomer consists of two or more words, then the name of the monomer appears in the parentheses in the name of the polymer. So polystyrene doesn't have parentheses because the name of the monomer is styrene. It's just a single word. But for methyl methacrylate, if we take methyl methacrylate and form a polymer from it, it's two words. So we put parentheses around it. Teflon is a trademark for polytetrafluoroethylene. So there's the example in that table below. Plexiglass is trademark for polymethyl methacrylate. The bad thing about plexiglass is if you need to drill a hole in it, you need to be real careful. Because as you drill your hole, it's just as likely to send a crack off like that. Whereas Lexan won't do that. Lexan is polycarbonate. And that's a trivial name too. PET nomenclature. All right. Terephthalic acid, ethylene glycol, polyethylene terephthalate. So that's in parentheses. And this is not a copolymer because terephthalic acid, ethylene glycol, they do not polymerize. Okay. Now we're going to look at properties of polymers. I know do you need a break?
No, okay.
Okay. As I mentioned early on at the very beginning, we are now engineering materials in our environment at the molecular level. So many polymers are designed to have specific properties for specific functions. And in doing so, we consider a number of properties, but two main ones in particular. Thermal transitions. And that where we're talking about phase differences. At what temperatures do they change from one phase into another? Or do they make certain types? It may not be a complete phase change, but at what temperature do we see transition from one type to another? And then solubility is another. There are two types of solids that we've looked at those in general chemistry, chapters 10 and 11. Crystalline versus amorphous. So you have a general idea of what we mean by crystalline as a regular ordered structure of the solid, whereas amorphous has no repeating units. It's all just a jumble. Let's see. So here's characteristics of amorphous solids as opposed to crystallines. Crystalline solids have well-defined melting points. So if you take an inorganic solid like sodium chloride, or, well, I don't know, take your pick. Sodium chloride's a good example. It's a crystalline solid. When you determine its melting point, it will be a very sharp. You heat it over time as it gets hotter and hotter and hotter and hotter. And then you see the transition from phase, one phase into the other. It happens at a specific temperature all at once. Whereas with amorphous solids, they have phase changes, melting points, in this case, over a wider range of temperature. An amorphous solid like is glass. It's composed primarily of silicon dioxide and some other additives, but it doesn't have a well-defined melting point. If you've ever seen glass blowers, when they take chunks of glass and throw it in the furnace, if the camera stays on it long enough, you'll see the glass just kind of start to sag before it turns into a liquid. The transition happens over a wide temperature range. This is known as the glass transition temperature, above which they become rubbery or viscous. So that sagging in that chunk of glass is the glass transition temperature. So you can assign a melting point for an amorphous solid, but the glass transition temperature gives you a better estimate of where things are actually changing. Above the glass transition temperature, the atoms in the substance have sufficient kinetic energy to move past each other, which is why the solid exhibits a loss in mechanical strength. I suspect that this is one of the problems that we saw with the World Trade Center when those jets impacted and the fuel blew up. It started heating up the steel structure, and the structure went through a glass transition temperature where it was weakened. And once it was weakened enough, the building collapsed. It didn't have to completely melt. It just had to lose its strength. Okay, crystalline polymers versus amorphous polymers. Crystalline polymers generally are able to lay close to one another. They have very low entropy. And we can look at it that way. They have low entropy, or if they are close enough to each other, they have the opportunity for their pendant groups to interact more widely, or if they don't have a lot of pendant groups like polyethylene, right? It's just a straight carbon chain with hydrogens on it. Then if it can lay close enough, then those intermolecular forces have more opportunity to attract the two together. And that will generally increase its melting point also. Whereas amorphous regions of a polymer, and these things can happen in the same polymer, you can have crystalline regions, you can have amorphous regions. So they can have both a melting point that is characteristic of the crystalline structure because it's easily discernible in a trace. And then with the amorphous regions will give you a glass transition temperature. The glass transition is usually at lower temperature than melting point. All right. So what's the effect of crystallinity on the glass transition? Well, it's important for actually, once the polymers are made, once the plastics are made, they're generally, the manufacturer tries to put them in some kind of form that's easily transportable. Like they may form them in little pellets. And that way they can be loaded into tanker trucks and transported and easily removed at their destination. And then they can also be easily brought to the processing area and fed into the machines, because a lot of these plastics are destined to be molded into different shapes. So if they flow easily as pellets, and then we know at what temperature they lose their structure and they can be formed. We don't need to completely melt them. We just need for them to lose their mechanical structure just enough so that we can inject them into molds and then let them reset. So the glass transition temperature is probably the more important for that purpose. Now these are, let's see what they're called, thermoplastics. They become plastic, they become malleable with heat. Whereas some polymers are thermosets. In other words, you heat them up and they set. I mean, they become rigid. Okay, so here we have an example of a die with Lego blocks, right? Synthetic polymers can be molded into useful objects. Most of them can be. Thermoplastics, there you go, can be heated above their glass transition temperature, or if necessary, you can take them to their melting point and forced into molds, push through slots to form films or threads. That's how fibers are for threads are formed for clothing or cloth manufacture. You take a synthetic fiber and push it under high pressure through a die with little holes in it, then it comes out the other side as little threads. You just need to be able to control what happens on the other side. Kind of like making spaghetti. Have you ever used well, you probably did, because when I was working in food science, we had this kitchen area. It was about half again as big as this room, and it had various types of equipment in it. One of them was an extruder, so we'd put our mixture inside, and it had a screw thing, and it would screw and force it under pressure through a die. And then you could either do it manually with a scraper, or as it came out, you could scrape it off and then dry it like you were making spaghetti.
Yeah.
And we had a flaking machine. It had a drum, and we ran steam through it. And we had this feeder, and it would feed the material onto that drum, and it would rotate. And as the drum rotated, it would dry it. And then on the other side, there was a knife that just peeled it off, and your flakes would come off like that. We used to make formulations for fish food that way with our shrimp and crawfish processing waste, try to figure out what to do with it for the businesses that were producing all that waste. You know, what do you do with it before the EPA gets hold of you? Anyway, we had lots of machinery like that. It was fun to use, but not much fun to clean up. Okay, intermolecular interactions in polymers. Okay, the type of intermolecular interaction becomes stronger as we become more polar and even ionic. So polypropylene has a glass transition temperature of -18 degrees. If you put a polar component in there, polyvinyl chloride, PVC, right, then its glass transition is 87 degrees. So now it becomes more suitable as piping. Or polyacrylic acid, right, as even higher because it's more ionic. It's more polar. Hydrogen bonding available. And then if you go to ion-ion interactions where you actually form the polysodium acrylate, then you can get very high temperature stability. Polymers with more branching tend to have lower glass transition temperatures and melting points because they can't lay close to each other, and those forces then aren't as active. The London dispersion forces, if nothing else, works. So if we have this polyvinyl N-butyl ether sticking off there versus the polyvinyl methyl ether, then the one on the left has the bigger side group on it, bigger pendant. It has a lower glass temperature versus the vinyl methyl ether. Regularity. Okay, so isotactic polypropylene that has its chiral centers are all the same all the way down the molecule. Has a melting point of 179 degrees. Whereas atactic polypropylene has no true melting point. My guess is that it maybe decomposes. Very regular structure on the isotactic polypropylene. Okay. Well-defined melting point. Atactic lacks regularity. Okay. So it's doesn't have a well-defined point and is tacky at room temperature. Okay. So it doesn't decompose, it just becomes tacky. So here's peak polymers rigidity. Okay. If we can introduce bulky groups that tend to limit the movement of the molecule, bending and rotating, then we can increase its melting point. So peak has a very, very high melting point, 365 degrees Celsius, versus polyethylene terephthalate, 270 degrees. So that's probably one of the reasons we use peak in our equipment. It's very rigid. It's very chemically stable. And it has a very high melting point. We're limiting by making the polymer chain rigid. We're limiting the number of isomers, conformational isomers. Okay, let's see. The main chain of peak is entirely conjugated. Is that true? Yeah, probably so. It has to jump over, let's see, with that oxygen in the ether position, it has it has two pairs, lone pair electrons on that oxygen, that ether oxygen. So if it's going to be conjugated with both of those phenyl rings, it must have overlap on both across that oxygen. All right, I'm trying to figure out why they're saying it's completely conjugated. The ketone, yeah, that makes sense, the way it's conjugated. I'm not too sure about the ether group. And then the PET, on the other hand, has portions of the main chain that are conjugated and portions that are not. Okay, yeah, we show they're highlighting the portions that are not conjugated. That makes sense there. It's a break. You have isolated conjugated systems, whereas for peak, the entire system is conjugated. And conjugation tends to to limit the movement of the chain. All right. How about pendant groups? Oh, we got a Newman projection here. Let's see. Think back. How is this going to behave? For polyethylene, that Newman projection is going to not be much of a problem. But if we put bulky groups on there, like polypropylene, we put that methyl group in there instead of the hydrogen, now we get interference in rotation because those methyl groups are bulky. All right, so we limit the rotation. That increases its melting point. Simply from steric strain, steric hindrance of movement. Okay, solubility. All right, that was one of the things that we designed polymers to do. Are they soluble? What are they soluble in? Are they soluble in aqueous solutions or non-aqueous solutions? Right? Polystyrene dissolves in toluene. Polystyrene. Okay. Yeah. What's that thing we used to do? We take foam pellets made of polystyrene and gasoline,
Yeah, and it
put them
melts
into
it.
gasoline. Yeah, melt it. And that's one of the ways to make napalm, I think. It's not the only way. Napalm is very specific. It's napalm is derived from the words of naphthic, naphthalic acid, and palmitic acid. Has some other things. But yeah, I mean, and you can make the bad thing about it is it makes a sticky mess. So if you throw a Molotov cocktail with some gasoline polystyrene in it and it hits something, when it breaks, it spreads and holds on while it burns. That's what's bad. Polyvinyl alcohol, on the other hand, dissolves in water. That's because it's got all these groups hanging off of it. Right? Hydrogen bonding. So polyvinyl alcohol is water soluble. Polymers with ionic side groups, such as that sodium acrylate, dissolve even more readily in water. Cross-linking tends to limit the interaction between solvent molecules and the polymer, which decreases their solubility. So that tells me that they would become definitely not water soluble with cross-linking, and probably just as likely to not be soluble in non-aqueous solvents either.
They got this new packing peanuts where you just run water over them and they dissolve. That way it's more friendly.
Okay. That makes me wonder, where does that go then?
Yeah, well, I mean, yeah, if it's going in the water supply, then what's it going to do to the water supply?
Yeah, you still got those polymers there.
Yeah.
Yeah, it's a test of marketing.
Yeah. People probably don't think about that. They probably just think of the waste.
Yeah.
Not landfill, but they don't think about the waste that's going in our water that goes in
Yeah.
our bodies.
That's why everybody needs to come take my courses.
Yeah.
I need to market myself that way.
Yeah.
Do you really know what's going into your water supply? But unfortunately, a lot of quote environmentalists are extremists. They make things worse than they really are. Sometimes, yeah, you need to be careful with certain things, but other times, it's hysterics.
Yeah.
Okay, highly crystalline polymers also have low solubilities because the solvent doesn't have access to them. It's a matter of surface area, I think. Crystalline regions tend to have strong polymer-polymer interactions, yes. Difficult for the solvent-polymer interactions to occur. And that goes back to our discussion of the process of solubilizing, right? Remember where you have three-part, you have the solvent and the solute You have to break them apart first, and then you put them back together. The third part. You take the same logic here. Okay, we're moving along. The relationship between structure and function in materials for food storage. Okay. So polyolefins are good choices for food storage because they're both insoluble, impermeable to water, impermeable to air, and they're inert. So we get saran wrap is a polyolefin. I'm not sure what kind of polyolefin it is. Polyethylene is the simplest polyolefin. Now, sometimes, especially where carpets are marketed, when they say your carpet has polyolefin in it, if they say polyolefin, that means they could put any one of these polymers in it. Right? So it makes it easier to, probably cheaper, as long as the physical characteristics are predetermined by the manufacturer, then they can make up a complex polyolefin as long as it behaves a certain way for the manufacturer, then they can make fibers out of it. So when they say polyolefin, it could be anything. Low density polyethylene. Low density polyethylene has lots of branching, which means that it keeps the main chains separated from one another. And if you take the same mass in more volume, that's low density. Linear low density polyethylene is a new one on me. I didn't know about that one. High density polyethylene would be very linear and packed close together. Now, some of these are not just dependent upon the structure of the polymer, but on the manufacturing procedure that aligns the fibers a certain way. Okay. Linear polymer chains result in maximum crystallinity. So high density polyethylene would be good for things like milk jugs. They need to be strong enough to hold the product. Low density polyethylene probably wouldn't work very well. Now, high density polyethylene is synthesized using the Ziegler-Natta catalyst because it controls branching, prevents branching, actually. These two guys, Ziegler and Natta, they got a Nobel Prize in chemistry for their work with this catalyst. So it's significant. You don't get a Nobel Prize. Well, it used to be. You didn't get a Nobel Prize for just throwing your name in the pot, and then along came Obama, and he throw his name in the pot, and he gets a Peace Prize for doing nothing. Yeah. Maybe that's why they gave it to him, because he didn't do anything.
It's amazing.
Let's see. So high density polyethylene has a higher melting point, has higher tensile strength, and it's more resistance to stretching than low density polyethylene. Makes it suitable for applications where low density would fail, such as milk jugs or other containers. Polyethylene polystyrene. Okay, low density polyethylene. Linear low density polyethylene combines the characteristics of low density polyethylene and high density polyethylene. And it does so by limiting the branching. So we've got a little example down there. The branching decreases the density, but the linearity, in addition to the side branching, gives you properties that are characteristic of high density polyethylene. So we copolymerize the thing with ethylene and a small percentage of alkenes. And this you have to use a special catalyst to do it. The end result of that is you get a product that has the strength of the high density and the flexibility of the low density, which is great for trash bags. All right. Polystyrene is not flexible, right? Due largely to those phenyl groups that increase the barrier to rotation. They stabilize the chain. So the glass transition point for polystyrene is much, much higher than it is for polyethylene. Right? Polystyrene has a higher density and it's more rigid. So it's good for things like razor blade handles. Here's polyethylene terephthalate. What we're illustrating here is the mechanical preparation of the plastic when it's molded. It starts off with lots of twists and turns. But during the molding process, we straighten things out and we get a unidirectional stretching that aligns the fibers. So whereas the pellets that go in, well, actually it's a slug. They put a slug in there and then they inject it with gas and stretch it out to match the mold. And when they do that, they get a linear unidirectional stretching that strengthens it. So it's stronger after the process than it was before. It's kind of like, not exactly like, but analogous to working metals. A smith will heat up the metal, which makes the crystal structure more amorphous, and then work it. And as he works it out, the crystals are aligned to one another, and they become actually harder, even at the same temperature. Can't work them anymore, so you got to stick it back in the fire. But it aligns the crystal structure, analogous to the polymer alignment, to strengthen it. All right. Let's see. Maximizing crystallinity increases the strength and decreases permeability. Okay. So PET has 4 times the tensile strength of high density polyethylene, more than twice the tensile strength of polystyrene. Interesting. I always knew that my pop bottles were rated to 100 psi. That's why we never go over 60. And we only do it once because you get stress cracks eventually. I had one blow up. I didn't learn my lesson. I'd used a bottle several times in the same experiment, and one of them blew up right at the cap right here. There must be more strain there than anywhere else, and it sounded like a gun. Fortunately, nobody was injured. But after that, we use them once, cut them up, throw them away. Okay, going green. All right, here's the recycling symbols. Resin identification codes, RICs. So they're arranged in order of 1 through 7. And the higher the number, the more difficult the polymer is to recycle. So number 1, PET is extremely recyclable. No problem whatsoever. So those pop bottles, you can turn those in. They can get rid of them. They can remake those pop bottles. High density polyethylene is a little more difficult. Polyvinyl chloride, a little bit more difficult. Low density polyethylene, polypropylene, polystyrene is very difficult. And other plastics, including nylon, polycarbonate, and acrylic, others are under 7, and those are very difficult. In fact, I've got a report that I pasted on my wall in my office, saying most of the stuff that you recycle, if you're an avid recycler, put it in the recycle bin. Most of it goes in the landfill.
Oh, really?
Yeah. They pick out the stuff that they can recycle easily, throw the rest away.
What about paper? I guess it's a lot easier to recycle paper.
Paper, yeah. Paper has lots of good uses, and of course, aluminum cans, no problem with that.
Yeah.
You just throw it in the furnace and start over again. And it saves a lot of energy because aluminum oxide is extremely stable compound. It takes a lot of energy to smelt the aluminum out of aluminum oxide. That's why the Alcoa and other aluminum manufacturers locate in areas where the energy is cheap. Like in the coal fields of Pennsylvania, along the Tennessee Valley, where you can get cheap hydroelectric power. That's where they located. And it was cheaper to ship the bauxite up from Puerto Rico in barges and to where the energy is cheap. Where were we? Oh, recycling things. Yeah, paper. Paper is easily recyclable. They even are good at recycling old tires.
Yeah.
I've seen them in the fatigue mats that you can stand on.
Oh, yeah.
Uh-huh. So there are two ways to recycle.
Which is crazy because you pay landfills to take your tires and they send off your tires. And I'm assuming they get money from it.
If they're good businessmen, yeah, they sell the tires to recyclers. And if the recyclers are available and close enough,
Yeah.
because you can't get them everywhere. I don't think West Virginia is really good at recycling.
Yeah.
I mean, we have some supposed to be able to recycle some things at the Beckley landfill, but I don't know what it is around here.
Yeah.
You have even an option for that.
We used to have a recycling center, but I don't know. I mean, this was when I was like really young, so I barely remember it.
Uh-huh.
So I don't know if it's still around or not.
Okay, after the plastic has been properly prepared, and that requires sorting. And in the beginning, sorting was all by hand. You just had a conveyor belt and just dozens of people standing there pulling and putting them in bins. Now they've managed to do some recycling, which is automated. Right? They can remove all the metal fairly easily. Even if it's non-magnetic, they can use a process called eddy current and remove the metals. And they can definitely remove the paper. And then the plastics probably have to be sorted by hand. So what do you do afterwards? Well, mechanical recycling leaves the plastic essentially intact. So in mechanical recycling, once you've got the polymer isolated so that it's uniform, one polymer, then you can run it through a grinder and make small pieces. That's more easily to transport or easily recycled at the end user. Chemical recycling degrades the polymer into subunits. Now, these subunits could be the same subunits from which the polymer was originally formed, or they could be different subunits, in which case those would become monomers for a different plastic. That's chemical recycling. Biodegradable plastics, most of them are not. Most plastics are not biodegradable. And very few of them are made from renewable sources. So most of the polymers that are biodegradable are the esters, the amides, and the ethers. they are more easily attacked by enzyme systems from microorganisms, bacteria and fungi. Let's see. Most synthetic polymers are derived from petroleum sources, either natural gas or oil, and which is not renewable. There's been some progress made in developing polymers that can be synthesized from renewable sources. Our example at the bottom is just that type, where you have the polylactic acid. Anybody who's ever exercised after being sedentary for a while knows what lactic acid is.
Yeah.
It's sore muscles. But once you get the lactic acid, then you can polymerize it. Actually, it's not the lactic acid that's polymerized, it's this lactide, which is a component of corn. It is biodegradable, definitely. Now, our last topic is biological polymers. I mentioned these some time ago, I think. These biopolymers come in 3 flavors. Proteins, and the subunit in the protein is amino acid. We call them polypeptides. The peptide bond is a special kind of amide bond. Okay, we won't go into that because if you're going to take biochemistry, you'll get a snoot full of it anyway.
Yeah.
Large carbohydrates, such as polysaccharides. They're called polysaccharides because saccharide is derived from the word which means sugar. So you take sugars and polymerize them, you get polysaccharides. Nucleic acids are made from nucleotides, and they come in 1, 2, 3, 4, 5, maybe 6 flavors. 4 main ones. For a DNA, you get four types of nucleotides. For RNA, we substitute one of those 4 with a different one and form the polymers. Now, why does the cell form these polymers? Different reasons. It depends on their purpose. For proteins, proteins or polypeptides, proteins are produced for different things. They are structural or motion, right? Like muscles. Structural would be like ligaments and tendons. Enzymes. Most of the enzymes are proteins. So they control reactions. Now, when a protein is being formed by the cell at the ribosome, the sequence of amino acids, and you'll have to memorize those too for sure. There are 20 essential amino acids and a few others that are not essential. The primary structure is just the sequence of amino acids in the polymer. So that's like the backbone. Sequence is the primary structure. Once you get the primary structure, and actually when the protein is being formed at the ribosome, as it's being formed, its primary structure is determined, and as it comes out of the ribosome, it assumes its secondary structure. Secondary structure has been identified as either an alpha helix form or a beta pleated sheet. Alpha helix just means that single chain coils, and it's held together mostly by hydrogen bonding in that coil. The pleated sheet, same thing, right? Either the same molecule can bend over on itself like this, and then bend back and forth, back, form the depleted sheet, because the way the sp3 hybridized carbons go, you have to do this, right? Because they're tetrahedral. Or you can get a pleated sheet arrangement between two neighboring molecules. That's secondary structure. Tertiary structure is further bending of the molecule. And essentially what we're looking at is, well, I should say beta pleated sheet is just the single molecule. If we put two molecules together, we're talking about another step. So the tertiary is further bending of the molecule into different shapes. The primary reason that a molecule will do that, form that tertiary structure, is so that the in an aqueous medium, which is the inside the cell, in an aqueous medium, the hydrophilic parts of the molecule are facing out and the hydrophobics are facing in. That's one reason. The other reason is that the protein, since it's got to perform these various structures, it needs a certain shape. The molecule has to be a certain shape in order to be biologically active. Now, it's a little more difficult to understand activity in terms of structure and motion. Well, motion, yeah, right, because you have protein fibers that slide past one another in a muscle. But enzymes, definitely. The structure, the tertiary structure, will determine activity of an enzyme. The common theory behind activity, enzyme activity, is the lock and key model. So the molecule that's going to be the substrate has to come along and find an enzyme that's got a shape where it can fit in. So there's the lock and the key. And then that then modifies both, usually, not always, both the conformation in the structure, bond strain and whatever on the substrate, plus the enzyme will change also. And sometimes it needs to do that in order for another reactant molecule to come in and attach itself to another part of the enzyme, so that then you can get a reaction between the substrates. That's a very oversimplified description. So this is tertiary structure. Okay. So we have to fold in a particular way. Quaternary structure. Quaternary structure is where you get a single protein that has established tertiary structure, and then two or more separate protein molecules combined. They attach to one another and produce activity. The best example I can think of is hemoglobin. Hemoglobin has two alphas and two beta proteins that are attached to one another, and each one of those proteins has an iron-based heme molecule in the center. And that's where the oxygens attach. So each hemoglobin molecule can attach 4 oxygens. And there's another example, enzymes. Right, the naming convention for enzymes, you'll get a snootful of that too. Now, that was proteins. Polysaccharides, or polymers that are composed of sugar subunits. Polysaccharides. So this particular polysaccharide looks to me like it's alpha-1,4 glycosidic linkage. This is starch. One of the types of starch molecules. This one is amylose. And they, polysaccharides. So I'll get the spell this right. Two C's. Polysaccharides come in two flavors. Either storage molecules, and what we mean by storage is energy storage. They store energy for times when the cell needs it, or structural. Okay. Amylose is an unbranched polymer of glucose. Makes up about 20% of starch, which is a storage polysaccharide. Starch. And it has a helical structure, extensive hydrogen bonding capabilities, which makes it very soluble in water. Amylopectin, on the other hand, is 80% of starch that is also composed of glucose, but it has branching. About every 25 or 30 units will get a branch. So this alpha 1,4 prime glycosidic linkage is essential for the definition of starch, along with alpha 1,6 glycoside linkage for the branching. The reason that's important, this alpha linkage, is that our enzymes can break that linkage and release the glucose for energy. I'll show you in the next slide, I think, where you can get a beta linkage. Beta linkage has the oxygen linkage on the other side. That would be called cellulose. Notice the difference in the position of that oxygen instead of being down here. Actually, for the alpha linkages, all the glucose molecules, see there, the chair conformation is pointing in the same direction. All these oxygens are pointing up, like that. In the beta linkage, you're getting alternating, the way it's written, you're getting alternating oxygen up, oxygen down. So the beta linkage is a different structural linkage for cellulose. Cellulose is structural. For the plant that produces it, it's structural. Now, if a fungus comes in there with the enzyme systems that can break it apart, then it becomes storage, right? And we can eat cellulose all day long and get nothing from it except for bulk, because our enzyme systems cannot break that beta 1,4 linkage. They can break the alpha 1,4 easy, but we can't break the beta 1,4. Termites can't either. So they have symbiotic organisms in their gut that has the enzyme systems to break it. That's why they can eat your house up and turn it into food. They couldn't do it without the fungi in their systems. Oops. Oh, that's it. Oh, yeah. A discussion of nucleic of DNA and RNA is too much for this course. So we're going to leave that for biochemistry.